Hello! Today I'm going to talk about Lee's third theorem and in particular the correspondence between Lie algebras and Lie groups. We will use our special friend SO3 and investigate how these groups and algebras are related. Okay, so we're going to start off looking at rotations in three-dimensional space. Then we'll look at how we form infinitesimal generators of the rotation matrices, and then how we can use these generators to form any arbitrary rotation matrix. Finally, we're going to generalize our result to show a correspondence between any Lie groups and Lie algebras. Firstly, suppose we have a vector sitting somewhere out there in three-dimensional space. Now to describe this vector physically, we first fix a basis for our x, y, and z axes. Once we've decided on this basis, then we can represent the action of rotating that vector around any of the three axes through these three matrices. To find what the vector looks like after the rotation, we simply multiply the vector by the corresponding rotation matrix. For example, if we want to rotate a vector 90 degrees around the x-axis, then we let theta equal 90 degrees and we multiply the vector by Rx of 90 degrees. Notice that in those three earlier rotation matrices, entries were either a 1 or a cosine or sine. Let's see what happens when we only rotate our vector ever so slightly around any of these three axes. Do you remember the power series expansion of the trigonometric functions? Good. Well, in our matrices, we had the cosine and sine of an angle. So if that angle becomes infinitesimally small, then any squared terms of the angle in the power series expansion go to 0. So we can therefore represent the rotation matrices as these three guys here. In each case, the diagonals are just 1s, so we can take out an identity, and we are left with these three antisymmetric matrices. Just for fun, let's then take those infinitesimal rotation matrices, subtract the identity, and multiply by the reciprocal of the infinitesimal angles. We call these matrices the generators. Do they look familiar? Yes, they're the basis elements of the Lie algebra SO3. Well, this is odd, isn't it? We started with some three-dimensional rotation matrices, looked at what happens to them for infinitesimally small angles, and played around with the results until we came up with the bases of one of our well-known algebraic friends. So how would we go from these generators to a matrix which can describe any rotation, not just around a simple axis? Well, first of all, the collection of all matrices which describe rotations about the origin in three-dimensional space form a group called SO3, with the operation of composition to maps. But how could we form this group? Let's take a closer look at our generators. First, recall the power series expansion of the exponential function, 1 plus x squared on 2 factorial, etc. By this definition, we can easily exponentiate a matrix, since simple matrix multiplication can achieve the powers of x. Now what happens if we exponentiate a generator? Let's consider the Rx generator multiplied by the angle of rotation, which, remember, is an antisymmetric matrix. By computing the powers of the generator and combining terms, we ultimately end back up at the rotation matrix around the x-axis. So our Rx generator, which is a basis of the SO3 Lie algebra, can become the rotation matrix around the x-axis, which is therefore an element of the SO3 Lie group, using the exponential map. Wonderful, isn't it? But hang on, this is just rotation around a single axis. How would we represent any element of the Lie group, that is, arbitrary rotations around all three axes? Well, remember that the Lie group's operation is composition of maps. And if the exponential of Rx times theta gave us our rotation matrix, can we just multiply the three matrices together to form this composition? Yes. Suppose we want to find the matrix which describes rotation around the x-axis by theta, the y-axis by phi, and the z-axis by psi. By composition of maps, we simply multiply the three matrices together. And by the nice properties of exponentials, we can just add the exponents together. You can even define a vector of generators and vector of angles and represent the rotation matrix by the exponentiation of the dot product between the two. Now that we've seen this correspondence between the SO3 Lie algebra and the SO3 Lie group, we can appreciate Lie's third theorem. The theorem states that every finite dimensional Lie algebra G over the real numbers is associated to a Lie group capital G. So what we have discovered for SO3 is not unique. Any real finite dimensional Lie group will have an associated Lie algebra. This theorem was first proposed by Lie himself in 1888, but it wasn't until 48 years later that a global proof was first provided by Cartan. One nice application of this theorem relates to the study of particle physics. The various symmetries in particle physics can often be represented by Lie groups. Rather than studying the representation theory of these Lie groups, it can be computationally simpler to study the representation theory of the corresponding Lie algebras instead. Thank you for listening.